Hey everyone, and welcome back to The Explainer. I am so incredibly pumped to have you here today because we are going to explore the absolute magic of motion. We're going to take something you do and experience literally every single day, completely deconstruct it, and then build it all the way back up. We'll start with just a tiny fixed point on a map and work our way up to the actual math behind that weird physical jolt you get in your stomach when you speed up. Okay, let's dive right in. Picture this. You're cruising down the highway, and there's this massive truck right in front of you. Stamped right on the back, it clearly says, keep a safe distance. We've all been there, right? It's a high-stakes, real-world dilemma that we deal with all the time. But to genuinely understand what's happening here from a physics perspective, we kind of have to ask ourselves a very specific question. So how much distance do we actually need to maintain from that truck to avoid a crash if it, say, completely slams on the brakes? And hey, does that safe distance change depending on how fast we're going? Well, to figure that out, we actually need to hit pause, take a step back, and strip the entire concept of motion down to its bare bones absolute basics. So, here is our roadmap for today. 1. The magic of motion. 2. Describing position. 3. Distance versus displacement. 4. Speed, velocity, ancient math. And 5. The feeling of acceleration. Starting off with part 1, the magic of motion, starting simple. You know, before we can analyze something as chaotic as highway traffic, we have to start small. Whenever scientists want to figure out a really complex puzzle, they always study it in its most idealized, simplified form first. And the absolute simplest kind of motion, that's linear motion, just motion in a straight line. Think of a car moving along a perfectly straight stretch of a desert highway, or a train locked onto a totally straight track. We call this one-dimensional motion. No turning, no swerving, just forward or backward. Which brings us to part 2, describing an object's position, finding our place. Okay, so before we can even talk about how an object is moving, we first have to map exactly where it is in the first place. And to describe a position, we absolutely need a fixed reference point. In physics, we usually just call this the origin, or simply O. From that origin point, position is defined by 2 key things: distance and direction. Now, since we're only looking at 1D straight line movement right now, direction is incredibly simple. It's literally just a plus sign for forward or a minus sign for backward. And when does an object officially have motion? Very simply, it's when its position relative to that origin point changes over time. Moving on to part 3, distance versus displacement, the runner's dilemma. Now, this introduces the exact friction point where I see so many students first get tripped up. Let's create a visual map in our heads. Imagine a track athlete. Step 1, she starts right at the origin at 0 seconds. Step 2, she sprints forward, hitting the 100-meter mark at exactly 10 seconds. Step 3, she immediately pivots and turns around. And step 4, she runs back along the exact same path until she reaches the 40-meter mark, completely stopping at exactly 16 seconds. Now look at the massive difference in these 2 numbers. The total distance she traveled is 160 meters, right? That's 100 meters out plus the 60 meters she just ran back. That is the actual physical ground she covered with her feet. But her displacement is only 40 meters because relative to where she started, that origin point, she's only 40 meters away. Let's take a second to really let this core terminology sink in. Displacement is officially defined as the net change in the position of an object between 2 given instants of time. Frankly, it does not care about the scenic route you took. It only cares where you started and where you ended up. And crucially, it requires both a numerical value, which we call magnitude, and a direction. And this naturally leads us to a really beautiful categorization in physics. Physical quantities that only need a magnitude, like that 160 meters of total distance we just talked about, are called scalars. But quantities that require both magnitude and a direction, like our 40 meters of displacement in the positive direction, those are called vectors. Remember those plus and minus signs we talked about earlier? Those are literally the heartbeat of vectors on a straight line. All right, part 4, speed, velocity, ancient math. How fast? Let's escalate things a bit and grab our next building block. We have distance and we have displacement. Now we are going to add the element of time into the mix. I actually love this example straight from the source material. The concept of speed has obviously been around forever. Just take a look at this problem from the Genikaka Shamudi. It's a massive mathematical text from 14th century India. It goes like this. 2 postmen are 210 yojanas apart, a yojana being an ancient unit of distance. Postman A walks 9 yojanas a day. Postman B walks 5 yojanas a day directly towards him. So try to mentally calculate this. In how many days will they meet?
If you guessed 15 days, you absolutely nailed it. But how do we actually get there? Well, by combining their efforts. Together, they're closing that gap by 14 yojanas a single day. 210 divided by 14 gives us 15. And this brilliantly illustrates the basic concept of average speed, which is simply the total distance traveled divided by the time interval.
But wait, remember how distance and displacement were totally different things? Well, speed and velocity are different in that exact same way. So the absolute crucial takeaway here is this. Average velocity is the change in position, the displacement, divided by the time interval. And because it relies on displacement, velocity cares deeply about direction. It's a vector. Let's anchor this with a super relatable example. Imagine Sarin goes to a 50-meter swimming pool. He swims from one end to the other and then all the way back again, taking exactly 50 seconds total. He covered 100 meters of distance in 50 seconds, so his average speed is a solid 1 meter per second. But what about his average velocity? Well, he ended up in the exact same spot he started. His displacement is mathematically 0. Therefore, his average velocity is literally 0 meters per second. Which brings us to our final section, Part 5. The feeling of acceleration, experiencing the jolt. Okay, we've reached our final escalation. I want you to genuinely try to recall a physical, sensory feeling for a second. When you're sitting in a car and it suddenly punches the gas from a standstill, you feel a noticeable jolt pushing you back into your seat, right? And when it suddenly slams on the brakes, you feel a jolt throwing you forward. That physical feeling is a change in velocity. And we measure that jolt with our final term for today, average acceleration. It's officially defined as the change in velocity divided by the time interval. And because velocity includes direction, acceleration does too. It's generally measured in meters per second squared. And this completely explains how acceleration vectors actually operate in a straight line. If you're speeding up, the magnitude of your velocity is increasing. That means the acceleration is pushing in the exact same direction as your velocity. But if you slam on those brakes to avoid that huge truck we saw earlier, you're slowing down. Your acceleration vector is literally pointing in the opposite direction of your velocity, fighting against it to bring you to a complete stop. Wow, okay, we have covered a ton of ground today, building everything from a single point of origin all the way up to the feeling of acceleration. But before we wrap up, I want to leave you with a provocative thought directly from the text to test your brand new foundational physics knowledge. Think about your car's gas tank for a second. Does the fuel used in a vehicle depend on the total distance traveled or its displacement? I mean, if you drive all the way to work and then back home, your displacement is 0. But is your gas tank magically full again? Yeah, I'm going to leave you to ponder that one. Thanks so much for learning with me today, and I'll catch you on the next explainer.